Good morning, class. This is Melody Rondo, and I'm going to be walking us through our lesson on tests about a population proportion. We did start this lesson already, so I'm going to scoot forward. We do have our learning intention and success criteria there, but I'm going to scoot forward through what we did yesterday. We talked about, the conditions, and we did an example testing out the conditions. And so this is not in your notes, I'm fairly confident. It's just something I wanted us to look at quickly. It says when we're talking about normality, confidence intervals, and significance tests, so what we did in Chapter 8 and what we're doing now in Chapter 9, they're both based on the sampling distributions of statistics. That would be, if you recall, sampling distributions are when we do a whole bunch of samples and then calculate a particular statistic from each sample and take that statistic, like, I don't know, if I took the average height of all the students in a class, or if I was trying to find like the average height of all the seniors, and then I did a bunch of random samples and found the averages for all of those samples, and then I put all of those averages onto a dot plot, for example, that would be a sampling distribution. Anyways, that is both use probability to say what would happen if we use the inference method many times. So both confidence intervals and significance tests are based on doing something many, many times. If the null hypothesis is true, then the sample proportion, since we're working with sample proportions right now, would vary according to an approximately normal sampling distribution. It's just kind of a background thing. All right, so jumping more into significance tests, we have the test statistic, which is what we're going to be looking at. With confidence intervals, we had the point estimate and our point estimator. This we're going to use a test statistic. So recall that a test statistic measures how far a sample statistic diverges or is different from what we would expect if the null hypothesis were true in standard units. That's a very fancy way of saying that we're going to be substituting the value from the null hypothesis for p hat, which we kind of saw this very briefly when we were writing our hypotheses. And here's the formula that we would use. The test statistic equals the statistic minus the parameter over the standard deviation. If you are not sure what that means, it basically means we're doing a z-score. So z equals p hat minus p naught over the standard deviation of p hat. So essentially, for these pieces, the p hat, this is of course from a sample, and then the p naught is what we expect to be true. This is from our null hypothesis, so just kind of pointing that out. And then the standard deviation from p hat is of course the standard deviation for the sample. I'll just jot that down as well. This is for the sample. And then I'm sure you probably need some time to write that down if you haven't already. So take a minute and do that. And I'm actually going to pause our video. All right, so let's jump into example 2. In a simple random sample of 53 free throws, the basketball player made 32. Calculate the test statistic, find the p-value using table A, which is our z-table, or technology, and interpret it in context. So, just to make that super clear, when it says table A, this is talking about the z-table, and technology means a calculator. And that was precious, sorry. Calculator. Wow. Really doesn't want me to write calculator. There we go. Okay, so to get started for this, if we're going to be doing the test statistic, we need to make sure we're clear on our hypotheses. We saw this in the previous example. So previously, we said that the null hypothesis, actually it was given to us, this is being super weird, sorry guys. Okay, it said that the null hypothesis was p naught equals 0.8, because they said they'd got 80% of their free throws, and the alternative was that we think, not equal, we think it might be less than that. So, sorry, getting crazy here with my pen, that the alternative is that P naught is really less than 0.80. Cool. So to get going on this, to calculate that test statistic, we're going to be doing basically a z-score where we're going to fill in our formula p hat minus p naught over the standard deviation of p hat. All right, so to fill that in, first of all, we're going to need to know what p hat is. So a quick reminder, we were told that the number of trials is 50. And so p hat would essentially be, from the trials there, we had 32 shots that they made out of 50. So we could leave it as a fraction, or we could turn it into a decimal. In this case, putting it into all those formulas, a decimal is going to be much easier. So again, that just came from the problem. And so let's go ahead then and plug it in. So I have my 0.64 from the sample. The suggested proportion is the 0.80. And then my sample standard deviation, because we're going to do this using a calculator, I'm going to plug in the formula for standard deviation and plug in the numbers to the formula all at the same time. So this is basically P, it's going to be P naught, so which is 0.8 times 1 minus P naught. Actually, I'll write that out so we are clear. And then over the number of trials, which was 50. So that we would put in our calculator and get a handy dandy z-score of something like negative 2.8. I have 2.843, but you guys should be trying that out on your own. Double check and make sure that we agree on that, although you can't tell me if you disagree because it's a video. Oh well. All right, so I get, when I round that to do a z-score to look it up on the z-table, I get negative 2.83. So then, being clear on what that means, of course I'm going to draw my normal curve, and I have my mean, and I'm looking at a z-score of negative 2.83 would be somewhere over here. And remember, when I looked that up on the z-table, it's going to give me this area. And the question, of course, is, well, what is that area? Is that the area I want? And we do, because our alternative hypothesis, remember, we steal the direction from here. It says less than. So we definitely want the less than side when we look it up on the normal curve. So I'm going to look that up on the normal curve, and I'm going to find an area of, looks like 0.0023. And so that area is a probability as well. And I just want to remind you, when we're doing a significance test, that we are looking for the p-value, which equals a probability. It's the same thing, but we say p-value now because we're fancy. And so essentially what we just did is we found the probability that our sample p-hat, so our sample proportion, would be less than or equal to the 0.64 that we actually found in our sample. And that probability is 0.0023. That is our p-value right there. And of course we could do that with the calculator as well. Just a quick reminder about how to do that. We would do, I believe the path is menu, stats, distributions, then it would be normal CDF. It's normal CDF for sure, whichever path it is to get there. There's a couple ways. And then what we would put in would be, we want the low end, so it would be like negative 10,000. And remember, don't put any extra commas in there. And then up to negative 2.83, which was our z-score. and then 0 and 1. We would do, yes, okay. And so this is our start, our stop, and then our mean. This is the mean, and this is the standard deviation of a standard normal curve. This is me doing it with the z-score, obviously not the raw data over there. And we would again get 0.002327. So very similar answer. We have that same first part. All right, so there's both methods for you really quickly. What we would need to say then is it says interpret it in context. So here's how we would interpret that. That statement, I'm sorry, my brain stopped for a second. Okay, if the player makes 80% of his free throws. Okay, so that part is the null hypothesis. So we're assuming if the null hypothesis is true, there is a 0.0023 probability of getting a p hat, so that sample proportion, there's a, sorry, the probability is of getting a p hat that is like what we got in our sample, so of 0.64, and I'm going to say or less, because that was the direction again of our alternative hypothesis, by chance alone. And then in the context here, in a random sample of 50. There we go. Let's go forward. You can pause it, of course, if you need to. But let's go forward. All right, so the 4-step process for significance tests, it's the same state. And I believe on this slide, what I would like you to do is write down what's in blue, but I'm not 100% sure, so you guys might have to make sense of that. So we're going to state the hypotheses we want to test and at what significance level, so you have to say what alpha is. And then define any parameters. Maybe I was just emphasizing that if we say we want to find the true proportion, we have to say the true proportion of what. And same thing if it's the true mean of what. I'm sorry, we're testing in this one, not finding, but same difference. Planned, we're going to choose the appropriate inference method and check conditions. The do step, we're going to perform our calculations if we have met the conditions. And those calculations are compute the test statistic and find the p-value. And then our conclude is where we say we reject or fail to reject the null hypothesis in the context of the problem. And you guys might want to pause to catch up since I probably went faster than you could write. And let's go forward. Number 3. On shows like American Idol, contestants often wonder if there's an advantage to performing last. To investigate, researchers selected a random sample of 600 college students and showed each student the audition video of 12 different singers. For each student, the videos were shown in random order. So we would expect approximately 1/12 of the students to prefer the last singer they view, assuming the order doesn't matter. In this study, 59 of the 600 students preferred the last singer they viewed. Do these data provide convincing evidence at the 5% significance level that there is an advantage to going last? All right, so let's jump into our state. Here goes. For the state step, we are going to say we want to test, because it's a significance test, we want to test the hypotheses So then we state what the hypotheses are. So here's where we would write that. So I would say H naught is that according to this, the what we would expect part, what we would expect is that approximately 1/12 would prefer the last student. That is going to be our proportion, or our P naught is equal to 1/12. Versus the alternative is that what we're trying to prove is that there is an advantage to going last. So that would mean that the proportion that prefer the last person would be greater than 1/12. And then we have to say what that P naught is, because we introduced P naught and we haven't said what it is in our problem yet. So we would say where P, the P we're talking about, is the true proportion of people, actually I'm going to say of students, because this was done with students, not just, I mean, students are people, but it does say the students. So the true proportion of students, and I might even be more specific and say college students, but that's all right, of students who prefer the last contestant. And then the last thing, like when we did confidence intervals, we had to say the confidence level. We have to make sure we say the alpha, the significance level. So here I would say if we prefer the last contestant, at an alpha is equal to 0.05. They gave us that 5% significance level up here in the problem. Significance level. All right, so that is our state. Then we go to plan. Our plan is that we are going to do a 1 proportion Z test. Before we would have said a 1 proportion Z interval when we were doing confidence intervals, but now it's a significance test, so it's a Z test. And then our check step, we're going to check the first thing is always random. Did we have a random sample? And the answer is yes. They told us they had a random sample. Cool. Then the 10% condition. And we're going to check that out. That would be n is less than or equal to 0.10 n. Our number of people that we sampled was 600, less than or equal to 0.10 n. That would end up, when I divide both sides by the 0.10, I would get 6,000 is less than or equal to n. And is it reasonable that there are more than 6,000 college students? I would say that's reasonable. So just a comment here that this is college students. So yes, that's reasonable. And then the normal condition, we don't want to forget that one. Normal, we are checking large counts when we're doing proportions. And so we're going to have here, this is going to be n p naught greater than or equal to 10, and then n 1 minus p naught greater than or equal to 10. And so I'm going to check that out. My n is 600. My p naught is 1/12. And I'm checking if that's greater than or equal to 10. I get, that gives me 50, which is greater than or equal to 10. Hooray. Then over here, I would have 600. 1 minus p naught is going to be 1 minus 1/12, so that would be 11/12. But your calculator can do that work for you. We get 550, of course, greater than or equal to 10, which that is. So we have met our conditions. On to the do step. Here's where we get to actually see the process all together. So I'm going to calculate that test statistic. Z equals p hat minus p naught all over the standard deviation of p hat. And so I'm going to plug in those values. For p hat, because 1/12 isn't very friendly, I would put that into a calculator. I'm not 1/12, I'm sorry, that's p naught. P hat, we didn't really talk about p hat really quickly from the problem, the sample they had for p hat. They had a sample size of 600, and they said 59, here it is right here, 59 of the 600. So that would be 59 over 600, not 100. And I would definitely turn that into a decimal, and most of the time that's going to be a bit easier to work with in our equations, but that is our p hat. All right, so I turned it into a decimal, so that would be 0.0983 minus our p naught, which as a decimal is 0.083, all over my standard deviation, which is going to be that fabulous formula. So I'm going to just use the formula here. My p naught is 0.083 times 1 minus 0.083. There we go. All over the number of people, or the number of, the number of people in this case, or the number of trials was 600. When we do that fabulous math, and yes, you should be trying this out on your calculator, I get 1.36. Again, double checking that on the normal curve, what that means here. A 1.36, here's the mean. That means our z-score is out, well, not that far out, geez, that's like 3. 1.36 would be closer to the mean. Something more like this. So that would be z equals 1.36. I'm looking for the area underneath, and I do want to pay attention. It's going to give me this area when I look up the z-score, but is that the area I want? If I look at my alternative hypothesis, I want greater than. I want p naught to be greater than 1/12, so I'm going to go with the greater than. So the area I actually want is this one over here. So when I look it up, though, I'm going to get this one. So if I do that, it looks like I get, my numbers are really small. I get an area of 0.9131. So to get the one I actually want, I have to do 1 minus 0.9131. And that gives me an end result of, so that equals my 0.0869. And this would be the probability that we would get a sample that is greater than the one we got, which was 0.0983. So that is our p-value. So this would be the result of our test right here. And I'm going to move on to the next slide to do the conclude step, but that would be our p-value. So that's really important. That's the p-value because it's the probability. All right, so let's go forward onto the next slide so I can give you the conclude. All right, so conclude. The conclude is where we start off with the p-value. So we just said that p-value equals 0.0869, and then I'm testing it and comparing it to the alpha value of 0.05. That's our alpha. And so that's the very first part of my conclude, is to decide if it's greater than or less than. This is greater than. So if it's greater than, are we going to reject or fail to reject? A greater than is fail to reject. So I would say we fail to reject. Fail to reject, where'd I go? I'm sorry. We fail to reject our null hypothesis, which is, we fail to reject. Try that again. The null hypothesis, which is P naught equals 1/12. And we say we do not have convincing evidence that the true proportion of students who prefer the last contestant is greater than 1/12. And remember that was that they have an advantage to going last. That was the whole idea of 1/12. Sorry, I don't need that there. Yeah, so I think that's it there. That finishes our conclude